Welcome to the first lecture in Lesson 2 of Chapter 2, and we are talking about the solar system. And we're going to look at a little bit about the history of the astronomy of our solar system, and then we'll talk about the formation of the solar system. And as the week goes on, we'll get a little more in-depth to the formation of some of the objects in the solar system, but we'll start just by giving an overview of what the current scientific model is. Now, we've talked a little bit about this. Mankind has been noticing patterns in the stars since the beginning of civilization. We've looked up in the sky and we saw these bodies moving, and we started to recognize that there was some kind of system to it. It wasn't just random. These things had a pattern, and so they started recording this. And so all the way 4,000 years ago to the second millennium BCE, one of the first planetary tables that we know of was written in Babylon, and it's called the Venus Tablet of Amisaduqa. And I'm probably mispronouncing that, so don't worry about that. But this is a record of the movements of the planet Venus. And you see it's a very old tablet. It's written in cuneiform, but it's pretty accurate for its time. And so this just kind of gives you an idea that us looking to the stars and noticing these movements, it's nothing new. It goes back so many thousands of years ago. Fast forward to 87 BCE, and you have what's called the Antikythera mechanism. And this is the world's first known analog computer. And what it did was it was a very complex orrery, meaning it was a model of the movements of objects in the night sky. And it was most likely used for navigation. This was actually found in a shipwreck not that long ago, and it kind of took them a while to figure out what it was for, but that's what it was. It just modeled the movements of different objects in the sky. And think about that. That's over 2,000 years ago. They were able to so accurately model that they could build this mechanism and use it for navigation. Now, most people at that time, with a few exceptions, believed that the Earth was the center of the solar system, really the center of the entire universe, but definitely the center of the solar system. And this is called the geocentric model. Geocentric, geo meaning Earth, center, centric, so meaning the Earth is at the center. And there were some exceptions, as I mentioned, to this, and we'll talk a little bit about it. But by the year, by the year 150 CE, Claudius Ptolemy wrote in his, completed his Almagest, and it really kind of codified the astronomical knowledge of his time. And he included in it a model of the solar system. You see right there, Earth being at the center and everything else moving around it. And now we can look at that and think, oh, that's so ignorant. But these were brilliant men, and they were doing the best with what they had. No one had been in space. They didn't have the advanced, even mathematics that we have now. So this was kind of the prevailing thought of the time. And this is what most people in the world, in most regions, believed until about the 16th century, when Nicholas Copernicus, in 1543, published his version, his model of the solar system, and it was a heliocentric model. We know that helio, back from talking about our Greek word origins, helios meaning sun, so heliocentric meaning sun is at the center of our solar system. This is the modern, current understanding of our solar system. Now that we've actually been into space and we have seen workings and we've sent things out, which is why we call it solar system. Solar referring to sun, everything else is a system around it. So all the way back in 1543, Copernicus said, no, this is not how it works. And he envisioned this heliocentric model. Now, in 1609, so the early 17th century, Johannes Kepler kind of started out laying out the laws for movements of planets. He said these things can't just be random, and so he came up with his 3 laws of planetary motion. So the first said that each planet has an elliptical orbit around the sun. So you remember we talked about an ellipse. It's not a perfect circle, it's more of an oval, and instead of having one point at the center, an ellipse has a 2 foci, that's plural for focus. So the sun would be one focus, and then there would be another, but it would move in this oval around. So a second law says that an orbiting object will take the same amount of time, and if you look at this picture here on the slide, it will take the same amount of time to travel between points A and B as it will to travel between points C and D. And this has to do with the aphelion or aphelion and the perihelion. Remember, the point furthest away from the sun and the point closest to the sun. And then his third law, the law of harmonics, says that the square of a planet's orbital time is proportional to its average distance from the star, cubed. So we're not really going to get into these. This plays a lot into physics, but I want you to understand what the thinking was when they saw these objects in motion. They said there has to be some kind of science behind it. It can't just be random. And then in 1687, Sir Isaac Newton publishes his Philosophia Naturalis Principia Mathematica. And so he took Kepler's laws of planetary motion and applied the understanding of universal gravitation to it. And he laid this foundation for the heliocentric model of the solar system. Guys like Copernicus and Galileo, at that time, this thinking was radical, and they were condemned for this belief. People said this goes against our understanding of science and of religion, and so they were deemed as unscientific and heretics and all of this. And now by the time of the end of the 17th century, you have Isaac Newton publishing these works, and people said, nah, these guys are right. This science is sound. And so they all said the sun has to be at the center of the solar system. And so that's the way it's been for the last 300 years. We've built on Isaac Newton's understanding of planetary motion, and we've built on Copernicus's heliocentric model. And now I want to talk a little bit about how our understanding of how the solar system formed. So the most current model says that the solar system formed about 4.6 billion years ago. Now, the model that's most accepted is called the nebular hypothesis, or solar nebular hypothesis. So the idea is that there was a nebula, a cloud of gas and dust in space, and gravity pulled this cloud together, and it formed a star because it got smaller, so it compacted, and it got hotter, and it began to spin. And that spinning is a very important part of it. The spinning is what's known as angular momentum. That's a word in physics. If you go into physics, you'll hear that a lot. And the idea is just it's constantly spinning in a circle. So this nebula had some angular momentum to it, and as it spun, this ball of gas compacted, but then it flattened out. It made a disk. And so if you see here in this model, you have your cloud, it compacts in one, and then it starts to become a disk. That's what gravity does. As something spins and it becomes more dense, it's going to have more gravity. And then that spinning is going to flatten everything out. So through the spinning, you get what's called a protoplanetary disk. And here are some pictures that actually the Hubble telescope took of protoplanetary disks it says in the Orion Nebula. These are pictures from NASA. You can actually see a lot of different things like that in their website. But as this nebula compacted and began to spin, you have a star forming, called a protostar, and it sends any material that's not collected into the star itself starts spinning around in this flat disk. And in this disk, that's where the planets are formed. And as I mentioned, we'll get into what actually, how the different types of planets formed and what they are. But this is the general model. So you see here, the star is forming, then you have this disk around the star, and that's where the planets are forming, and you have objects coming in and things colliding, and so you would have the dust coming together, and so gravity is still taking place here, but then as these objects become more massive, more dense, they start to get their own gravity and start pulling in things together there, and that's how the planets are forming. And so fast forward about 4.6 billion years later, here is our current understanding of our solar system. Now, again, these distances aren't to scale, obviously. You have at the bottom here a little more of the scale, but here's the relative sizes and their moons, and we'll go into these objects in a lot more detail as we go. But this is just an overview of our solar system, our understanding of it, and where it came from.